Good morning, sir. I am Rohini from Electronics and Communication Engineering Department, second year, and my subject name is Control Systems. And here my topic is on a numerical problem on lag compensator. Introduction to lag compensator. Before entering into my topic, first we need to know what is meant by a compensator. Compensator which have wide range of functionalities and variants, and these are essential components of control systems, and these compensators are nothing but an electrical system that is used to obtain the desired performance, and these compensators are mainly used to stabilize the unstable systems. In this compensator there are different types such as cascaded, feedback, and cascaded with feedback compensators. Furthermore, in control systems, there are three types of compensators are present. First one is lag compensator, lead compensator, lag lead compensator. Here, lag compensator. What is meant by lag compensator? This lag compensator is one of the type of compensator which is an electronic system which is used to introduce the phase lag at lower frequencies. This lag compensator is primarily used to improve the system steady state performance. It improves by reducing the steady state error without significantly impacting the transient response. And the key points of lag compensator are: first, it produces a sinusoidal output with a phase lag related to the input sinusoidal, and it introduces a control phase lag in the forward path of the control system, and it improves the steady state response of the system. Here, these are the steps to design a lag compensator. Here, we apply the above steps on a numerical problem. A numerical problem on lag compensator. The question is, the open loop transfer function of a certain unity feedback system is given by G of S is equals to K by S into S plus 4 into S plus 80. It is designed to have the phase margin to be at least 33 degrees, and the velocity error constant Kv is 30-second inverse. Design a phase lag series compensators. Here they given that velocity error constant Kv as 30-second inverse, and they given unity feedback system and G of S value. And first step is to calculation of gain K. We know that velocity error constant formula Kv is equals to limit S tends to 0, S into G of S into H of S. We substitute G of S and H of S values. We get limit S tends to 0, S into K by S into S plus 4 into S plus 80 into 1. Here they given that open loop transfer function, and it is a unity feedback system. So we get H of S is equals to 1. After that we cancel this S and substitute S as 0. We get K by 4 into 80, that is equals to K by 320. We now substitute Kv value as 30. 30 is equals to K by 320. From this K we get as 9600. This is the value of K. Second step is to board plot of uncompensated system. Here now we substitute this K value in G of S equation. We get K by S into S plus 4 into S plus 80. After substituting the K value, we get 9600 by S into S plus 4 into S plus 80. Here now we are taking 4 and 80 as outside. We get 9600 by S into 4 into S by 4 plus 1 into 80 into S by 80 plus 1. After cancelling this, we get 30 by S into 1 by 4 is nothing but 0.25 S plus 1 into 1 plus 1 by 80 is nothing but 0.0125 S. Now we are substituting S is equals to J omega in this equation. We get G of J omega is equals to 30 by J omega into 1 plus 0.25 J omega into 1 plus 0.0125 J omega. Now we are plotting a magnitude plot. To plot this, we need corner frequency. To get the corner frequency, we just reciprocate the coefficients of j omega. Omega c1 is equals to 1 by 0.25, which is equals to 4 radians per second, and omega c2 is equals to 1 by 0.0125 is equals to 80 radians per second. Now we tabulate one table. Here contains term, corner frequency, slope, change in slope in dB. First 30 by j omega. Here there is no corner frequency is present, and slope is minus 20. There is no change in slope is present. So minus. And here the second term is 1 by 1 plus 0.25 j omega. Here the corner frequency is 4 radians per second. Slope is minus 20. Change in slope is minus 20 which is equals to minus 40. Third one is 1 by 1 plus 0.0125 j omega. The corner frequency is 80 and slope is minus 20. Minus 40 minus 20 which is equals to minus 60. Here we select two frequencies, lower corner frequency and upper corner frequency. Lower corner frequency as 1 radian per second, higher corner frequency as 100 radians per second. Now we are substituting the omega values. At omega is equals to omega L, A is equals to 20 log 30 by j omega. Here j omega we are taking as 1, so we get 30 dB. At omega is equals to omega C1, here we are substituting j omega as 4, we get 17.5, which is equals to 18 dB. At omega is equals to omega C2, here there is a change in slope is present, so we use this formula, change of slope from omega C1 to omega C2 into log omega C1 by omega C2 at plus A, at which omega is equals to omega C1. After substituting the values, we get minus 34 dB. Here also same as previous one. At omega is equals to omega h, A is equals to change of slope into log omega h by omega C2 plus A, at which omega is equals to omega C2. After substituting the values, we get minus 40 dB. Now we are plotting the phase plot. For phase plot, we are taking this formula. Here the j omega is present in denominator. We take minus 90 degrees, and these all the values are present in denominator. We take minus as constant. So here we take tan inverse of imaginary part by real part. So tan inverse of 0.25 by 1 omega. Here minus tan inverse of imaginary part by real part. Tan inverse of 0.0125 omega by 1. We get this formula. Now we are substituting the omega values in this above equation. We get at omega is equals to 1, phi is equals to minus 104. At 4, phi is equals to minus 138. At 10, phi is equals to minus 164. 50 minus 207, 80 minus 222, 100, it is minus 230. Here I am plotting the border plot. On x-axis I am taking omega in radians per second. On y-axis I am taking A in dB, and it is the magnitude plot of the above values, and it is the phase plot. And here I am taking scale as on y-axis 1 unit is equals to 10 dB. On y-axis 1 unit is equals to 20 degrees. Here from this graph we need to determine the phase margin. Here we determine the phase margin at the magnitude plot, which is cut exactly at 0 dB line. We extend the point line to phase plot, and we measure the angle which is get as minus 168 degrees. It is the phase margin. Now we need to calculate the phase margin of uncompensated system. For this, the formula gamma is equals to phase margin of uncompensated system. Phi GC you are taking as phase of j of omega gain crossover frequency. We have the formula gamma is equals to 180 minus phi GC, which is minus 168 degrees phase margin, which is equals to 12 degrees. But we need to, the desired phase margin is 33 degrees, so we use this lag compensator. Step 4 is to choose a suitable value for phase margin of compensator system. Here gamma n is equals to gamma d plus E. Here gamma n is new one, and gamma d is desired phase margin, which is 33 degrees, and epsilon, which is 5 degrees. We substitute the values, we get 38 degrees. Step 5 is to determine the new gain crossover frequency. Let omega GCN is equals to new gain crossover frequency, and phi GCN is equals to phase of j omega at omega GCN. Now we have this formula, gamma n is equals to 180 plus phi GCN. To find the phi GCN, we take gamma n minus 180 degrees. By substituting these values, we get minus 142 degrees. From border plot, at minus 142 degrees, the phase plot cuts at this point. We extend this point to downwards. We get 4.7, which is new gain crossover frequency. Omega GCN is equals to 4.7 radians per second. Now step 6 is to determine the parameter beta. To determine this parameter beta, we extend this line to upwards, and we take the decibel value, which is get 16 dB, which is the magnitude value. A GCN is equals to 20 log beta. To find beta, we take 10 to the power of AGCN by 20, which is equals to 10 to the power of 16 by 20 is equals to 6.3. Now step 7 is to determine the transfer function of the lag compensator. Here we take the two values, ZC is equals to 1 by T and ZP is equals to 1 by beta T. Here T is equals to 10 by omega GCN, which is equals to 2.13. Here the general transfer function of lag compensator is DC of S is equals to S plus 1 by T by S plus 1 by beta T. Here we can also written as beta into 1 plus ST by 1 plus S beta T. We substitute these values, we get this formula. Here step 8 is to determine the open loop transfer function of compensated system. Here we drawing a block diagram of lag compensated system. We have this formula. Here in this block we take 1 by beta. Here GC of S, and it is G of S, which is nothing but a feedback system. Now open loop transfer function of the compensated system is here from the block diagram. The blocks are in series. We just multiply them, and after multiply them, we get this formula. Step 9 is to determine the actual phase margin of the compensator system. In this step, we check whether our problem is correct or not. Now we substitute S is equals to j omega in this formula. We get this one. Now we need to check the phase margin. So let phi naught is equals to phase of g naught of j omega, and phi gc naught is equals to phase of g of j omega at omega is equals to omega gc. And here it is an imaginary part which is present in numerator. We take positive tan inverse of imaginary part by real part. Here j omega is present in denominator. We take minus 90 degrees. At same as we here minus tan inverse of imaginary part by real part. We repeat for this formula. We get this one. Now we substitute omega is equals to omega gcn in this formula. We get these values. Phi gc naught is equals to this minus 147 degrees. Now we substitute minus 147 degrees in our formula gamma. Gamma naught is equals to 180 degrees plus phi gc naught. We get 180 minus 147, which is equals to 33 degrees, which is required phase margin. So in conclusion, we check these values, compensator system satisfy the requirement, so the design is acceptable. Thank you, sir.